Tom Quinn. How you can record. It gives me great pleasure to introduce my colleague, Derek Richardson. Derek started his astronomy career just a few hours drive that way in Vancouver at UBC, working on trying to find planets before exoplanets were actually found. So he goes back quite a ways. He got his PhD under the supervision of Sfera Arce at the University, sorry, I said PhD, his DPhil at the University of Cambridge. Okay, we gotta be clear about that. Under the supervision of Sfera Arce, doing N-body simulations of planetesimals. We hired him here as a postdoc to continue his work on N-body simulations, part of the N-body shop, and he was promoted to research professor during that time. But then University of Maryland hired him away, where he's now a professor there. And so his research over the years has been collisions of planetesimals with each other, the breakup of Comet Shoemaker-Levy 9 before it smacked into Jupiter, crater chains on the moon caused by collisions of small bodies. And now he's going to talk about us hitting back at those small bodies. So this is going to be absolutely wonderful. Thanks, Tom.
Oh, thank you, everyone. It's a pleasure to be back at the university.
All right, people in the line, so ready for it?
Wow.
There we are.
Yeah, it's different but the same. You know, so lots of people here that I recognize and had a great opportunity to meet up with again and get caught up on what's going on. 23 years is a long time. There's still plenty to talk about, so I'm glad we'll be able to hang out a bit more. So today I'm going to talk about the DART mission, which I was involved with. The mission is officially ended as of earlier this year, but there's still lots to learn, and there'll be a follow-up mission that I'll talk about. I just want to say at the outset that DART is a technology mission, not a science mission. It was meant to test the technology to deflect a potentially hazardous asteroid. We do not know of any such potentially hazardous asteroid at the moment for the next 100 years, so don't worry about that. And our experiment did not make our target dangerous to the Earth as a result of hitting it. Instead, what we succeeded in doing was demonstrating that the technology now exists to protect our planet in the event that there might be a hazardous object heading our way. So that's what I'll talk about today. I'll give you some background on what are the impact hazards, what the DART mission was, and what we actually accomplished. And go. Nope. Not going. What you just saw was video footage of the Chelyabinsk meteor as it impacted into the atmosphere in 2013, February 15th. This thing was about 70 feet across, going about 40,000 miles an hour, and it broke up at 100,000 feet altitude. It actually hurt about 1,500 people, mostly because they saw this big bright flash in the sky. And I thought, oh, that was interesting. Let me go look through the window and see what that was. And 20 seconds later, the window smashed in their face because of the sonic boom. So when you see a big flash of light outside, give it a moment before you check it out. It caused a lot of damage, about $33 million worth of damage. And we did recover some of the meteorite. I'm showing you, obviously, clips from the video that was taken. Don't stand near that door. So it was very easy to recover the meteorite because it's a big hole. This is only a portion of it, but the biggest piece ended up in that lake, and they sent some divers down and recovered it. Perfectly ordinary meteorites, just like the kind we have in our meteorite collections. But it did a lot of damage. And that's the biggest one we've had hit our planet since the Tunguska impact in 1908. And what we can say is that unless we do something about it, it will happen again. And this was a relatively big city, but fortunately it was a small meteor, and so it broke up high enough. I should also point out there was people hurt by glass, and 8 people were sunburned from being very close to the flash. It was directly above them, 100,000 feet. So here's our planet. We are basically a target in space, and the things that are coming after us mostly are the asteroids. And so just a reminder that most of the asteroids in our solar system lie between the orbits of Mars and Jupiter. And they are the leftovers of planet formation. So planet formation is not a perfectly efficient process, and still stuff left over that is flying around and occasionally can hit us. There are millions of asteroids out there. But if you were to scoop them all up and put them into one body, it wouldn't even be the size of our own moon. So there's not a lot of material, right? But there's lots of individual pieces. And they are all potentially dangerous. So today I'm talking mostly about asteroids or other hazardous objects out there like comets, and most recently we've discovered interstellar objects. We won't talk about those because those are a little harder to deal with, but we can in principle use the same technology to defend ourselves against those. So here's an example of a big explosion. This happened 50,000 years ago, the meteor crater in Arizona. How many people have seen Meteor Crater? It's awesome to visit. It really gives you a sense of scale. And you can see when this hit the surface, it would have generated a fireball that would have been about 10 kilometers in radius. It would have killed animals out to about 24 kilometers in radius. You would have felt hurricane force winds up to 40 kilometers. This object was only about 50 meters in diameter. That's pretty small. In fact, that's about the smallest you can get and still get through the atmosphere and hit the ground at full speed. So anything else getting to hit us would actually have to be larger than that. Our target, Dimorphos, is about 3 times larger than this guy. Oh, and of course, I come from the Maryland area, so it would have wiped out DC, which may or may not be a good thing. I love this plot. This is a plot of all of the impacts into the atmosphere that have occurred since 1988, as recorded by ultrasound sensors that are used to enforce the nuclear test ban treaty. And so we now have access to this data. It used to be classified, but now we've got it. And you can see asteroids don't care where they hit. North, south, east, west, night, day, doesn't matter. They'll hit us. And you may recognize the jelly bits on there. That's the big one. There it is. Oh, very quickly. Watch very closely in the upper right. So the good news for us is that big asteroids are rare, the ones that can kill off the dinosaurs. And we've more or less detected all of them that there are to be found. But the smaller ones are actually the more dangerous ones in the sense that they are more likely to, with more of them, so they're more likely to hit us, and we haven't seen them all yet. That's what's shown here. So there are about 5 million objects the size of Chelyabinsk. They'll hit us once every 100 years. And we've discovered about 0.4% of them. They're very hard to see, they're very fast and small. But this category is the one that we're really concerned with. It's 140 meters, causing enormous devastation over regional areas, not continental size, but still very bad. There's about 25,000 of those, and we've only found less than about half. So we're still looking for those, and there are missions underway. Concepts are going to be happening. ESA Hera, and of course the Vera Rubin telescope will give us insight into some of these potential impactors. So what can we do about this? So fortunately, this is an international effort to protect our planet. It's not just the United States doing this. The United Nations has committees and so on that are involved with these hazards. But fundamentally, it boils down to finding the hazards and defending against them, mitigating. And so the DART program has to do with that last part, mitigation. And it's part of the Planetary Defense Coordination Office, PDCO. This is a new thing that was just established in 2016. It's their budget that paid for the DART mission. How many people have seen the movie Don't Look Up? Yeah, you may not have noticed this. I was certainly attuned to it. That early on in the movie, they talk about the PDCO, and a big graphic comes up and says, "This really exists." That's the PDCO. So they didn't make it up. Don't usually see such flashy PSAs from NASA. Yeah, so we did it. I was at the mission control area, not in the mission control itself, but at Applied Physics Lab, which is the lead institution for this mission, on September 26th of last year, when we successfully hit the target. And the energy was amazing, right? I've never been to a live mission like this where you're waiting for that instant to know whether you succeeded or not. And it was a ton of fun. What they were saying in the video, we could have missed, was absolutely 100% true. None of this was guaranteed that we were going to hit the target, and that would have been quite the letdown. And what happened instead is we were about as close to dead center of the target as we could possibly have been. So it was a tremendous success. So what I'm going to do now is step you through the nature of the mission, what we're trying to accomplish, what we succeeded in doing, and then I'll give you a little bit of science background as well, instead of these just sort of general topic slides. So here's the idea. We have an asteroid called Didymos. It's about 760 meters across. Very fast rotator, rotates once in its axis every 2.26 hours. We just stand in the equator to pick up a rock and let go, more or less stay in orbit. It's so fast. In fact, its fast rotation is what we think led to the formation of its satellite called Dimorphos. That was the target of the DART mission. We want to hit a satellite because it's easy to measure the change in orbit of a moon going around a somewhat larger body than it is to measure the change in orbit around the sun. It would have taken a lot longer to measure, it would be in a much smaller percentage effect. So this was a great way to test this. This was the inspiration behind the mission led by Andy Chen when he thought of this. Scientist at APL. So the spacecraft came in, it's about 580 kilograms at impact. It was moving 6.1 kilometers per second. About 2 weeks before impact, it released Risha Q, a little CubeSat, and it was basically following just slightly off the same line as the original spacecraft to take pictures as DART hit, and then we would continue and see the otherwise unseen backside of Dimorphos so we could get a better sense of its overall shape. All of this was timed so that Didymos was close to the Earth, only 0.076 AU, so that we could use ground-based telescopes to see what happened, because of course, our very expensive and lovely camera was destroyed on impact. So there was no way to measure what we had done. One last thing, couple things. This is only about 1.2 kilometers separation, and Dimorphos itself, again, is about 150 meters. So one of these dangerous class objects with lots of them, and they would do a lot of damage if they hit us. It's a really good choice of target. There were 4 level one so-called requirements, the thing that NASA wants to accomplish to determine whether the mission was a success. Those were, we hit our target, that one. Second one was to change the binary orbital period by at least 73 seconds. And as you'll see, we did a lot better than that. We wanted to measure the change in period within 7.3 seconds accuracy, which we achieved. We're about 1 second accuracy in our measurement. And then we wanted to measure this thing called beta, which is the momentum transfer enhancement factor. So if we were just hit the spacecraft into the asteroid and nothing else happened, all that momentum of the spacecraft would have been delivered to the asteroid, and that's how much we would have pushed it. But when we hit something like this, we expect ejecta to come off. That ejecta acts as an extra jet, and that will give you an enhancement of the momentum delivered. And we were tasked with being able to measure that. And that fell into my category as the lead of the dynamics working group for the mission, to make sure that we actually got that measurement. Okay, and good news is, yeah, we did all of those things. So let me show you how that worked. So first off, here's our spacecraft coming in. We hit our target. It originally was on schematically this orbit. We put it into this slightly smaller orbit. The original orbit was 11 hours and 55 minutes to do one loop around. The new orbit, 11 hours, 22 minutes, a change of 33 minutes to the orbit. And that was measured within days of impact. Actually, we measured it sooner than we expected. We thought it would take a little longer because we thought it might be hard to get the signal out with all that debris, but the observers were amazing and got all that data very, very quickly. Give you a sense of scale. Largest building on Earth, about the size of Didymos. Here's our target, Dimorphos, and here's our spacecraft. And all of the mass is there, inside that little dot, the bus of the spacecraft. We had exactly one payload, which is the camera, and that is what smashed into this and changed its orbit by 33 minutes. Notice the little wings there, those are the rollout solar panels. The first time rollout solar panels have been used on the spacecraft, and they worked flawlessly. All right, next slide, please. Yeah, so this is what we thought Didymos would look like prior to encounter. And here is Didymos going across the sky. I'll make it easier for you so you can see. There it is. This is radar data. So you can send out radio pulses and measure the time delay and the change in frequency and get a shape and rotation of the target. That's how we knew roughly what the shape was and the fact that it had a moon. And it looks kind of like some other things. You've seen pictures of Ryugu and Bennu, which were asteroids encountered by other spacecraft. Kind of similar, this rotating top kind of thing. Turns out it's not exactly what it looked like. So here's what the system looked like 61 days prior to impact. That is Didymos and Dimorphos there. We blow it up so that you can see it there no better. I don't know why they thought it was a blow up picture. But anyway, that's our target. That was 61 days before. We were 20 million miles away. Here's what it looked like 4 hours and 5 minutes prior. So you can see that there's a few pixels across. You only see one object, you don't see the moon. The reason for that is the moon is behind the asteroid at the main body at this point. We knew that would happen. We very, very carefully had measured the orbital period and the phase, so we knew that at this point, we would not be able to see the moon. We had to wait until about an hour before impact before we'd actually start to see the moon. And so there's 73 minutes before. Can you see the moon? There it is. So when we were at APL, and we got this image, and we were like plastered up against a screen about this thing, and we're like, is that it? Is that it? Yeah, that's it. Very, very exciting. So it was right on schedule. It started to appear. Then this was at this point, we turned on the smart nav, which is the autonomous navigation to impact. And its job was to find the bright thing, ignore that, and focus on the faint thing and aim at its geometric center. Here we are, 50 minutes before the impact. We're 11,000 miles. Now remember, that's 18,000 kilometers. We're going 6 kilometers per second, so very, very fast. And the separation of the two bodies is only 1.3 kilometers. So And what we're gonna see next, I think we're gonna see a movie. Beep, there it is, okay. This is sped up a factor of 10 the last 5 minutes. At this point, we can clearly see the moon. The people in the mission control had 19 possible contingencies. They had a 30-second light delay, so they could step in and intervene if they thought the spacecraft was going to somehow target this. Instead, that goes Didymos off of view, but they didn't have to invoke any of the contingencies. That worked without human interference, straight in, and we're going to slow down the last frames. So what happened in that last frame is it was in the process of sending back the previous frame when it hit the surface. This is unbelievable. I mean, it just like high fives, everything was going on. It was so cool when that happened. Putting them both in the same frame so you get a sense, and kind of changing the angle here. So this is our big thing. Now notice it's much more squished than the radar model. So it's not the same shape as we expected, it's more oblate. Our target here, Dimorphos, looked kind of like what we expected. What I thought was, or a lot of us thought it was going to be prolate, meaning it's kind of hot dog shape and pointing towards the main body because it's so close it should be in tidal walk like our moon is to the Earth. This little blob here sticking out was a bit of a concern because we didn't want the spacecraft to target that. It turns out it's part of the main body. It's just a slight shadow here. If you stretch the image, you can actually see it walks all the way to that point. Well, it turns out this body is not prolate. We're getting fooled by the geometry. I'll explain that in a bit. Here's a close-up of Dimorphos. So you can see it is the quintessential rubble pile. So it's made up of loose rubble that has come together through its own gravity. Now, admittedly, we don't know what it's like on these. It's a reasonable assumption that it's like this all the way through the interior, but we can't rule out other possible internal geometries. And this is the last frame before impact. And we have named these boulders. They all have names. Those boulders, sadly, no longer are with us. And we didn't know what kind of terrain we were going to hit. Was it going to be smooth? Was it going to be big boulders? Was it going to be like just a solid surface? All of these were possibilities. So we had to account for all the possibilities. And this is why there's a lot of uncertainty is how big the beta would be, the momentum enhancement factor. Is like we don't know what the surface is going to be like. As it was coming, it was like, okay, we got ourselves a roll pile for sure. What's going to happen next? So they're able to reconstruct the geometry of the impact. And this is just microseconds prior to impact. And so we know that one of the solar panels hit this boulder first, and then the main bus, and then the second solar panel. And that's what happened. So this is Leisha Cube, our little CubeSat was watching, and these are before and after pictures, 6 seconds apart, showing the flash of the impact at the time on September 26th of last year. 3 minutes later, this is what it looked like. This blew us away. It's like, what are we looking at? So this is Didymos. The image has been stretched a lot to bring out the detail. All of this stuff is ejecta coming from Dimorphos. When I first saw that, I said, we killed the moon. I didn't see how it could possibly survive that. But it turns out it's just you're looking more or less down the ejecta cone as it comes towards you, and the rest of the asteroid is fine. It's like that. Although, turns out in the end, we probably did a lot more damage than we thought. Here's a whole series of stretches where we're stretching the least here and the most out here, so you can just see these tendrils as they come out. On this screen, you can't quite see, but there are discrete points of light, which are boulders that have come off, and those have been tracked. You can actually watch them move. And I'm going to show you a picture in a moment of boulders in space, which is pretty cool. But I said earlier, in order to figure out what happened, we had to have observers on the ground, not just on the ground, but you. There were a lot of them. And it was the job of the observing working group to coordinate all of these observations and bring them into one coherent story. We had telescopes on every continent, including Antarctica. We also had 3 assets in space: the Hubble Space Telescope, James Webb, and the Lucy spacecraft all took images of the impact. For James Webb, not to alarm you, but we're like, hey, can you guys take a picture of the impact? Sure. How fast do we need to slew the telescope? We have to slew it this fast. Okay, that's 3 times more than spec. Let's think about it. Yeah, sure, we can do that. It's like, okay, it only costs $10 billion. I'm sure it'll be fine. They were confident they could do it, and they managed it. It's pretty amazing. Here's what it looked like from the ground. So this one is an animation from the telescope in South Africa. And so you can see this amazing plume of material that came off the instant after impact. This is not rocks. This is some kind of vapor that's come off. We're still trying to understand the origin of this, but it's believed to perhaps be related to the xenon that was propellant on our spacecraft. And hydrogen that was not actually used. We didn't use the xenon. We had an ion thruster, but we didn't need it. So that's probably what that original puff was, which dissipated very quickly. But it's not the rocks. Those come later. Here are the images from Hubble and James Webb, moments about 5 hours after impact. So remember, there are diffraction spikes. It's like a cross for Hubble, and it's 6 spikes for JWST. But you can see there's definitely structure here that is due to the ejecta, which is kind of in this direction. This is forming the cone here, and here as well. And they could do animations of this and to see the structure in these different wavelengths. But this actually is my favorite picture. This is from the telescope, the SOAR telescope in Chile. And this is now 2 days after impact. And so now we're starting to really see the geometry of the ejecta. So let me put in some labels here. So DART came in this direction. And so this stuff is the ejecta cone coming out in that orientation. And now for the students in the room, which way is the sun? You student? That's your point. We made a comment. This is the cometary tail, and it is directly anti-sun. So the sun is in this direction, and the tail is pointing away from the sun. So this is being pushed by the solar wind radiation pressure from the sun. Absolutely classic. So we made a comment, and we weren't sure if, again, all of this, it's an experiment. I mean, this is our sandbox. What's going to happen? We thought, yeah, there should be a flash. There'll probably be some debris. There might be some kind of tail. We didn't know how long it would last or what the geometry would be or anything like that. So the days subsequent to this was just spent just looking at this system, obviously trying to measure the change in the orbit period of the satellite. You can't distinguish the 2 bodies here, but there's one, remember, there's 2 bodies in orbit around one another in there, plus now a ton of debris. More than a ton, let me tell you. At one point, this is 12 days after impact, the tail split. And it's still a little bit mysterious, but it's likely due to the fact that we had a binary system. So there's interactions going on that is churning this stuff up in a way that gives structure to the tail, which eventually dissipated. Here we are, November 18th. So this is now just shy of a month later. And this is a picture from the Lowell Discovery Telescope. And you can see this tail going off the screen, keeps going. And beautiful, very, very thin, and attached to the nucleus, we'll call it. Here we are, 83 days afterwards, Hubble Space Telescope. This tail is still massive, and we still have it attached to the front. Now, this was taken by Dave Jewett et al. When they got some time on Hubble. Dave Jewett is the master of active asteroids. This was his thing. So he took this picture. Those are not stars. Each one of those blobs of light are boulders that are co-moving with the Didymos system on this image. So we have an animation just showing those things moving. So we liberated massive boulders. Now, you're not seeing those are, of course, just points of light. They're not dissolving them, but they are nonetheless bright points indicating, yeah, there's a bunch of rocks that came off in different directions. And so there's a lot of effort going into trying to understand that. Here we are 147 days later, Lowell Discovery Telescope. You can still see the tail. Cool thing there. It's still there, still attached. 168 days later, and multiple images stacked, so you can really pull out the tail. Very obvious, still attached. And the very last picture we were able to take until Didymos got too close to the sun. So this was in July. HST tail still attached. So when it comes back around, we can get some more pictures. We're hoping to see, is the tail still there? And is it still attached? I keep going on about that attachment. It means if it's still attached, there has to be some continuous loss of material from the system. And it's not from the impact, that's long done, right? So there's material that is orbiting in the system between these two larger bodies that is just dynamically getting perturbed and gradually leaking out and still contributing to the tail after months. So, of course, the point of the whole exercise was, did we at least change the orbit? We clearly made a mess, but did we actually accomplish our original mission? And the answer is yes. And the way we found this is through actually a technique that many of you will know from exoplanet detections, from the transit technique, same idea. The alignment of the moon and the main body to Earth is such that it has mutual events. And we can measure not only in and out of the eclipse, but also as it comes back around, you'll see that the moon casts a shadow on the main body, and that can also be measured as well as these big dips. And so the timing between dips gives you a period. And so this rather complicated plot is meant to show you how we measured the actual change in period. So what we're showing here are two sets of arrows, the ones that are in orange and the ones that are in gray. Gray is where you would have expected those mutual events to have occurred if the orbit had not been changed. The orange ones are the ones that have best fit for the actual change in orbit. And you can see that the orange ones are lining up with the dips. From here, now this is much better to blow it up. So here's a dip, here's the orange one. If we hadn't changed the orbit, the dip should have occurred here. It did not occur here, it occurred here. If we hadn't changed the orbit, it should have occurred here, it did not occur, it was over there. And the solution for where the dips actually are is 11 hours and 22 minutes to even greater precision than that. So the difference is 33 minutes. So we changed the orbit by 33 minutes. This was, you can see the dates here. So September 27th is the day after. We didn't get any data because it was just too much of a mess. But within a day, they were already starting to pull out light curves despite all of that stuff happening. But the radar people said, screw you, we can do better than that. And so they had the first measurement within hours and didn't tell us. Like, we're gonna keep the secret. Can you see Didymos in this image? Radar data you take mostly on faith. This is Didymos. That is a multi-sigma detection, believe it or not, in radar space. So we're seeing this image is in delayed Doppler. So one axis is the time delay, and the other axis is the change in frequency. But this is actually very strong detection. And what's also amazing is Dimorphos is there too. There and there. And the cool thing is, just like for what I just showed you with the light curves, we know where it should have been if we hadn't changed its orbit, which is there. There are no points there. And this point is consistent with an 11-hour, 22-minute orbit. These points are where it would have been if it had been 11 hours, 55 minutes. So within hours of impact, the radar people had already measured the change in the orbit. Very, very, very cool. So nailed it, and we got a big change. What about that beta? So just a reminder, so what's happening is you're getting this momentum enhancement from ejecta coming off the target. There's no ejecta, you get a push due to the spacecraft alone. There's some ejecta, you get an extra push because of the ejecta. There's lots, you get an even bigger push. So what did we actually get? Well, it turns out, big whopping 3.6. So in other words, we delivered 3.6 times the momentum of the spacecraft into our target. This is very important for understanding what would it take to get a needed deflection of an asteroid. We can take into account the fact that, oh, we can expect a boost of several factors in that orbit change. The team had anticipated a value between 1 and 5 based on numerical simulations, but we were all saying, 2 is the conservative estimate. And we ended up with almost double that. So we were very, very happy. And the reason it's 3.6 is because there was a massive amount of ejecta. So remember, our spacecraft was 550 kilograms. We liberated 10 million kilograms of rock from the moon, which sounds like a lot. It's still only 1% of the mass of the moon, which is 10 to the 9 kilograms. If you'd like to read all about it, there was a special issue of Nature. So this is April 20th this year, and there are 4 papers in there. So the overall "we did it" paper, then the measurement of the period change that I showed you the data for, the fact that we had all that ejecta. This is basically the people who led the HST imaging. And then the paper I was involved in, which was measuring the momentum transfer and highlighting. So my student got second billing on this because he did a ton of work on this measurement. And there's Andy Chang, who conceived of the idea of hitting a binary as being the best way to measure this. So it really was an international team. We were meeting online and in person. This is Andy Chang here. These are the 3 leaders of the team. Nancy Chabot was the main team lead, and Rivkin was also the co-team leader. And there I am with my student, Harrison. All right, how are we doing? Oh, that's what I'm talking. Good. So as I said, I was the lead for the dynamics working group. So I'm going to give you a little bit of the nitty-gritty details of the dynamics without hopefully getting too deep into it, but I'm happy to answer questions afterwards. Let's start with this. So post-encounter results. So this has been submitted to the Planetary Science Journal. I got the reviews back this morning. I have some work to do. There's a cast of thousands on this paper, so it's going to take some time. So it likely won't appear in print until 2024, early 2024. So I remember how I said that we expected Dimorphos to be prolate, and it looked like that in the pictures. We were wrong. It's not prolate. It is in fact oblate. So if you imagine if you had like a hamburger and you're looking on an edge on, a little puffy in the middle, let's say, that's what Dimorphos looked like to us. And if we were to look at it rotated 90 degrees, it would be a circle. So it's a spinning disk rather than a hot dog. And this was not what we expected. So for technical reasons, which I'm happy to talk about later, we would have expected it to be prolate. So first mystery, don't really understand that. We have some ideas. So there's implications for how we form these moons. Because we didn't realize this was an oblate body, this explains why we didn't have any light curve measurements of the secondary before impact. They were looking for them, like, where is the secondary? Why can't we see it rotating or doing something? If it had a different shape, then we would notice something as it was going around the object. But we didn't, and that's because it was symmetric. So you couldn't measure that. Now, here's the fun part. The measurements we have post-impact from the light curves and from dynamical modeling of the orbit, which takes into account things like the precession of the orbit of the secondary around the primary, it's very likely we now have a prolate body after we hit it. We hit it hard. And so it's now axis ratio of about 1.3 to 1 is the best fit, which means we took it from being a disk to being something probably more like a kidney bean after the impact. So in other words, the crater is about as big as the object itself. And but we won't know for sure until we actually send another mission, and I'll get to that in a minute. So as I said, we changed the period by 33 minutes. 3 sigma error bar on that is 0.1 minutes. Line of expectation. So this meets all of our goals. We changed the speed of the orbit by 2.7 millimeters per second. That's how much we changed it, which is about 2% of the original orbital speed. So all the effects that we're doing here on this target are at the 1% or 2% level. But nonetheless, we were able to pull out all of this information. Here's our momentum enhancement factor beta at 3.61 value I told you earlier. Pretty hefty error bars. These are only just 1 sigma. Reason for the big error bars is we don't actually have a measurement of the mass of Dimorphos. And that's what you really need to know. Just, you know, we can see a change in speed, but to determine what the momentum change was, we need to know the mass of the target. We don't, so we're guessing. We're guessing the mass based on the total system mass, which we get from Kepler's laws, modified because it's not quite Keplerian, and the volumes which you get from the photometry, so you can see the shapes. And that gives us bulk density for the system. We assume that's the same bulk density for the small guy. That gives us 2,400 kilograms per cubic meter. And gives us the 3.61. But these are big error bars, so it could be a little bit more, or it could be a little bit less. Fun fact, that change in period was 33 minutes, except over the first 15 days, it dropped another 26 seconds secularly from the level down. And this is pretty robust there. And what we think we're seeing there is, remember how I was saying we had those double tails and stuff? We're seeing interactions between the binary and the ejecta. It's causing a little bit of binary hardening, causing the two bodies to come together a little closer, have a little faster orbital period, as a result of interacting with the ejecta before it got too diffuse for it to have any effect. And the conservative estimate is that we released 10 to the 7 kilograms of material, which is 1% of the moon mass, and the moon itself is about 1% of the system mass, subject to these uncertainties. After impact, the eccentricity of the system is 0.03. We don't know what it was prior. It could have been 0. It's actually consistent with it being 0. If it was 0 before impact, the circumstance of the impact would imply a post-impact eccentricity of 0.03. So it is consistent. Except, it appears to have gone to 0 briefly and maybe back up again, and so it may be chaotic. If it is chaotic, it means something is happening, exchanging angular momentum between the rotation of the bodies and the orbit in a way that could be very interesting for any follow-up missions. We squeeze the semi-major axis of the orbit by a few tens of meters. Now, lastly, what do we do to the rotation? We are not sure. As I'll explain in a moment, we 100% expected to induce vibration. What that means is, if it had been prolate, and you're going around like this, here's the camera, hold up, you're going around like this, pointing one end always towards the moon, at your particular orbital period, and then you do something to change the orbital period, you're clearly not going to be still aligned as a result. And so what's going to happen is you're going to wobble back and forth, and that we call that libration. It's a yaw axis rotation. So we believe that has certainly happened, and the data is consistent with that. But it may also be tumbling, meaning it may have lost, it may not be in principal axis rotation anymore. And but the trouble is, it also may have changed shape. And those two things turn out to be degenerate with each other in the light curves. So we don't really know. And so what we need to do is go back to the system. We're still looking, but it's hard to say. There was a suggestion that ejecta from the secondary could have landed on the primary and changed its rotation period. Remember, it's 2.26 hours, really, really close to breakup. It's so fast rotating. But we've measured that to within about 1 second of accuracy, and it's unchanged within 1 second. So we don't think any ejecta landing on the primary has caused landslides or anything else to dramatically change the orbit. All right, I'm going to probably skip the next few. Well, I'm going to do this. I'll do this one. This is in our pre-encounter paper published in PSJ. And we wanted to know how unusual is the dark impact for this poor little moon. Well, it turns out it's pretty unusual. So what we have here is a plot of impact energy and the impact interval for impacts due to other things around in the solar system. So let's focus on this one. So if we look at all the main belt asteroids and near-Earth objects that plausibly could hit Dimorphos, it would be on this curve. So the probability of impact as a function of impact energy is less and less likely as you get to higher and higher energy. On this plot, you can plot the dynamical lifetime, how long an object is expected to stay a near-Earth asteroid before hitting too close to a planet and being ejected from the system, hitting a planet, going to the sun or whatever. Well, it's about that. This was the energy of the DART impact. So what this is telling us is that in the lifetime of this moon, this is probably the worst thing that's ever happened to it. Sorry. That's kind of interesting. And we'll just skip the rest of the details. This is have a fun meeting. Faculty meeting for the faculty here. The rest of us can party. I won't go into detail. This is basically the calculation for how you get beta from the observables that we had. This is the change in the speed in the orbit, mass ratios and things are going here. So basically just ratios of the momentum. And this is showing our best fit. And here's that 3.6 value for an assumed bulk density of 2,400 kilograms per cubic meter. But you can see there's a lot of room for other possible values once we can really constrain that mass much better. So there's a lot of incentive to do that. And the final thing I want to show in this area is basically rotation dynamics is very complicated. So this is Harrison's work. As a function of the axis ratios of our body, notice these numbers are very, very close together. And one is oblate. So, you know, just slightly off oblate. Here's the measured shape of Dimorphos prior to impact. There are regions in this where the yaw angle, the libration, can actually exceed 90 degrees. That's where it is shown in white. So that would mean you basically started just free rotating. There are other places where you can also get in there. You can also look at the other axes, roll angle, nod angle, going up and down the pitch. All of those things have areas of possible instability that we may have just hit. Plus the fact that the shape changed so dramatically, we think, to 1.3, hello, like way off of this axis. We really don't know what we did. And so we need to send something back there in order to actually measure that. So that's what we're going to do. So next year, in October, there will be the launch of the European Space Agency's Hera mission, which will go back to the Dimorphos and Didymos system and do some measurements. So it will rendezvous at the end of 2026 and stay through 2027. This is what DART did with our optical camera. So this with CubeSat, we hit our target quite successfully. In 2026, Hera will launch with 2 CubeSats with a radar detector. We've got various cameras, spectrographs, and so on. And they're going to land things on the moon. They're going to do all sorts of great stuff. So it would be really nice if this had been at the system before we hit. So they could do before and after pictures. But unfortunately, the European nations, this is part of the optional program, they weren't so keen until NASA said, yeah, we're really going to go. And said, okay, fine, we'll send something. It was too late for them to get there before we hit. So they're going to go afterwards. But crucially, they'll get pictures of Dimorphos. And we'll see, is it tumbling? Have we changed the shape dramatically? What's happening? If it is tumbling, good luck landing your landers. Sure, we fine. They're a real challenge potentially. So we told them for months, guys, get ready for the possibility that this thing is not in a stable rotation, and you're going to need to think about how you would land a spacecraft. So that'll be a really interesting challenge. If you'd like to learn more, the website is still operating even though the mission's done. You can become a planetary defender by doing a quiz. We've got various hashtags and so on, and I will leave it there. Thank you very much.
Thank you very much, Derek. We have time for questions. Okay.
Oh, me?
Yeah, you go, yeah, go.
Yes, go ahead.
So, silly question, and this might be like more of like a sci-fi thing, but in my head, I was imagining like you'd send like, more of like a warhead kind of thing that would like explode to push it.
Right.
Like, why did you prefer like the ejecta, the momentum, rather than like a warhead like explosion?
Yeah, exactly. So, a conventional explosion, a little harder to control. So we basically, throwing a rocket something is old school warfare. So there's that. If we were going to deflect an asteroid using an explosive, we would most likely want to use a nuclear device. And the reason there is not because of the force of the explosion or anything, because there's no atmosphere. So what we'd be doing is we would detonate a device to create a heat flash that would vaporize the surface of the asteroid, creating a jet, just like as though we had hit it to create the jet kinetically. You create this jet through vaporization, and that will then also nudge the asteroid away. In very limited cases, it might be possible to disrupt the target through direct kinetic impact or nuclear explosive into the target. But generally speaking, most scenarios have you deflecting it by having it either direct kinetic impact or an off-surface detonation. Go ahead.
Can you explain how the ejecta increases the momentum? Like, how does the ejecta work? How does that move the asteroid faster?
Yeah, that's a great question. So I have a little quiz that I give some of my students, which is imagine Dr. Evil drops you on a perfectly frictionless sheet of ice, and you have no tools, just you, dressed as you are. How do you get off the sheet of ice? Throw something. So you take your shoe, throw it, and you throw it one way, Newton's third law pushes you the other way. So it's a practical application of Newton's third law. So the actual excavation process as you hit in is mobilizing material that is kicked off the surface of the asteroid, and that requires a force. And the force is counterbalanced by the equal and opposite Newton's third law reaction. Great question. Yes.
And can you explain, I'm having a tough time thinking 6 months later, you're still photographing it and it's still attached, this ejecta is still coming off of the same spot. Like, how does that work?
Yeah, so we don't think it's so the initial few hours it would have been ejecta coming out. It takes the dynamical timescale for interesting things to happen mechanically on the surface of the asteroid is done after a few hours. But you put a lot of stuff, a lot of it has escape speed from certainly the moon, which is measured in centimeters per second, and from the system itself, which is measured in tens of centimeters per second. That stuff is gone, it doesn't play any further role. But there's going to be some fraction of that material that has sub-escape speed. And so it's now in this gravitational system and just doing its thing. It's on some kind of orbit. Complicated because we've got these two bodies going, you've got other debris in there. So it just hangs around. But every now and then, one of those pieces will get too close to one of the bodies, get enough speed, interact with the second body maybe, and that slingshots you out of the system. And so gradually, you start to leak out those things that were able to stick around for a while, but not forever. So that's probably what's happening. Yeah.
How would the estimates done for the total number of meters in each size class? Like you said, you can detect 42% of whatever the class is. That's very scary. But how is the estimate done for the total number?
Yeah, that's right. So it's one of those. One of the ways we do that is we can look at a surface that we know has been hit a lot. And the best surface for that is the moon. And so when you look at the moon, you can see the distribution of craters on the moon. There's no erosive processing apart from little micrometeorites happening on the moon. So it's a very nice record, the history of impacts in our solar system over billions of years. And from that, we can literally just count craters of different sizes. We know there's a relationship between the diameter of an impactor and the size of the crater it leaves. And so we can see that there are maybe more small craters than there are big craters, for example. And you can start to plot that, and you actually get a pretty nice power law. And so you can then say, all right, well, I count this many kilometer-sized craters. That means I have to have this many 50-meter-sized impactors, for example. And then we go and look to see how many we detected. Well, we've only seen 1/3 of the expected number from our crater counting. That must mean that there's 2/3 we haven't seen. So that's more or less how that procedure goes. Yeah. Yes.
So I'm curious, supposing we found a comparable object like this tomorrow that was in a flight with Earth, do we understand the momentum enhancement well enough to be able to hit it and like not hit it? Because I get worried about keyholes because it's too hard or not, next time around, it might be very possible. Can we predict that yet, or is it still difficult?
Yeah, that's right. So, the first order, we're interested in the first impact. Right, so that's the one we want to avoid. You're absolutely right that it's possible to deflect an object in such a way that it misses the Earth, but it goes into a new orbit such that in close encounter with the Earth, nonetheless brings it back in a possible collision next. In which case you just say, okay, we've got to do it again, basically. So I don't know if people have heard of Apophis. So Apophis is an asteroid that will come by, I kid you not, on Friday the 13th of April, 2029. It will be within geosynchronous orbit of our planet. So it'll be interior to some satellites that we have in orbit around our planet. When it was originally discovered, it was given a 2% chance of hitting the Earth. They quickly discovered that, no, it's not going to hit the Earth, it's fine. But there's this possibility of hitting a keyhole. So a keyhole is basically a region of phase space, close approach distance and speed, that if you just hit it just right, you go into an orbit that can get you coming back and hitting the planets on some subsequent paths. And so for a while, we were worried about, we're going to hit the keyhole of this. And it turns out that's no longer possible either, thanks to the Arecibo telescope, which sadly is no longer with us. So we are partially blind because we don't have that facility anymore to help us with these sorts of calculations. So this particular, to answer your question, there are uncertainties. We don't, this was beta 3.6 for this particular setup. Would it be different for a different asteroid? Quite possibly. So what I believe, and a lot of people in the committee would say, is that, all right, if we see a hazardous object and we have time, the very first thing we should do is send a spacecraft to investigate. So a rendezvous mission, or reconnaissance mission, see what it is we're dealing with. Can we assess them by looking at it? Okay, does it look like a rubble pile? Does that mean that, okay, if we hit it, we'll probably get something like 2 to 3 times the extra kick? So we can design spec for that. And then we can look to see what deflection would that give? Are there keyholes? Okay, maybe we should crank it up a bit, so we just make sure we miss that. So those sorts of calculations can happen, but there will still be some pretty big error bars. So reconnaissance, follow up, and I would say, don't put all your eggs in one basket. Make sure you're ready to go with the second launch in case the first one misses, or if you do another nudge, those sorts of things. Just keep that capability in your pocket to be able to really make sure. Go one up there and one here first. Yes.
Said the crater was on order, like the size of the moon itself, right?
This is an inference that is consistent with the current light curve data. We don't have pictures.
Okay, was there, I mean, if that's true, was there any concern that it would break up this object?
Oh, I was very concerned. When I first joined the team, 2016, or something like that, I did a very simple calculation. I said, all right, what is the gravitational binding energy of Dimorphos, given our best guess of its size and mass? And that's all it depends on, size and mass. And what is the kinetic energy of the impactor? I know its mass and its velocity. And I'm like, oh, look, the kinetic energy of the impactor is about 100 times more than the gravitational binding energy of Dimorphos. And I told the people, are we concerned about this at all? And they're like, oh, that'll be fine. And the reason is that the energy gets deposited at the surface and mobilizes stuff at the surface very quickly, and because of the rubble pile nature of the object, does not transmit very efficiently to the rest of the body. And so there is a lot of energy delivered, but a lot of it goes to heat and kinetic motion of the target area and not the rest of the body. And so you can afford even 2 orders of magnitude more than the binding energy.
So that 580 kilograms, impact is that just mechanical parts, or is there like some tungsten slug?
Oh, right. Yeah, it was just mechanical parts. In fact, we had this thing called the Ion Next. So it was a experimental ion engine on board. And the plan had been to ignite it and take DART off of its perfectly ballistic trajectory to impact, by the way, just a flawless launch. We're gonna turn it on, deviate, and come back to the original orbit as a test of this system. But when they first were playing around with it, they noticed the power fluctuation on board, and they said, forget it, it's not even worth the risk. We never actually used it. So all of the fuel for that, plus the engine itself, was part of the mass that eventually was deposited into the target. So it was just free mass. Yes. Oh, sorry. I think I promised you next. Yes.
Did the CubeSat survive, or did the CubeSat that was following survive?
It survived for a little while, but then stopped communicating with Earth. But it survived long enough to get, I believe, 90% of its data down to Earth. This guy would be tiny, little box. 2 cameras called Luke and Leia. One of them was not very good, so Leia was not so great. Luke was pretty good. I just sent down data. Now the paper on the issue was supposed to be part of those 4 that went into Nature. It's supposed to be a 5th paper, but because of various technical difficulties and the delay in getting the data down and all this stuff, it didn't make the deadline for that. It is now actually the final revision to come out in Nature. I don't know if it's been officially accepted yet, so hopefully that will be in that's. And over, but yes.
You keep calling it a rubble pile.
Yeah.
I imagine it's a bunch of rocks glommed together, or is there like a solid core with rocks on top?
Yes. So we don't actually know, because we've never peered inside one of these things. So we have indirect evidence of homogeneity in some cases, like Bennu and Ryugu. There's no obvious indication that there are large cores in those objects. They've got pretty good gravity measurements. For Dimorphos, we don't really know. So it's possible one way or the other, we don't know. As far as how they're formed, so if the idea is that a moon of an asteroid forms through this accretion of material that comes off of the equator, then we would expect the size distribution of the stuff that forms the moon to equal the size distribution of the stuff that was on the surface of the Didymos in this case. And there's some big stuff, there's some smaller stuff, and dynamically speaking, the bigger things kind of push around everybody else, and they will tend to fall towards the center of an accumulating rubble pile. So my expectation is that if there is a bit of a size distribution, the biggest things are probably in the middle, but we don't know for sure. Now, the Hera mission, one of those CubeSats will have a radar on it, and that will be able to probe into the surface, into the interior for the very first time. No one's done this before. It's been proposed, but no one's managed to do it. We'll actually potentially get some information on the internal structure. Fantastic.
Very cool.
Before we go to, I want to just make sure do we have any questions online, Lisa? Nope, okay. Carry on.
In the back, and then here.
I'm thinking, the lead time here, so what, 58% undetected, 6 years planning, 10 months in space, and eventually a 1% effect. Putting all those things into the magic computer thing, when we detect the one that is gonna hit us at the, shortest time from detect to go, how much time do we have to put something together and make the right impact?
Yeah, that's a great question. So, we were budget limited on this. Presumably, if there is something coming our way, the budget limit would be cranked up a bit. That's one thing. So we could launch, more mass, for example. And we could also build it more quickly. Now, I will say, from the point at which we were given go to the point of launch was just a couple of years. 3 years actually, and we did delay. We went to the secondary launch window because of two problems. One, COVID, which delayed getting some parts that we needed for the spacecraft. And the second, so let's hope it's not, pandemic when we're about to get hit by an asteroid. The second thing was the mirror for the telescope, the camera, in the shake test failed. They realized it was not bolted correctly, so they had to order a new mirror because it was no good and had to rebolt it. So that pushed us 6 months later. And so, assuming we didn't go through those problems, we could have done it in about 2 years, which is pretty good. And as you said, there is a travel time as well. So let's say 3 years kind of minimum on that sort of, unless someone pours a lot of money into it, is what we could expect. And that's pretty good. And so for something about 140 meters, we would hope to have some lead time there. I will point out, Chelyabinsk, which was 25 meters, was not detected before impact. In fact, ironically, I don't know if you remember, but NASA had advertised, hey, there's going to be a really close approach of an asteroid on February 14th, I think it was, of 2013. Everyone should look over there. And we were looking over there. Bang! We got hit on the back of the head from Chelyabinsk. And they were completely unrelated. It was just a fluke that they happened to be close at the same time. So there's still this problem. Now, Chelyabinsk, one part of the reason why it wasn't detected was coming from the direction of the sun. And so we have a blind spot towards the sun, and so we need to have orbiting assets that are interior to our orbit in order to be able to detect those. So there's still work to do to build up our network of defenses, our detectors. But I think it's feasible for something that, if it's bigger than 140 meters, the bigger it is, the easier it is to detect, and the earlier we'll detect it. So I think we're getting very, very close to being able to deal with a lot of these things. But obviously, I better touch some wood now that I've said that. There's still plenty of room for things to sneak up on us. But I would say that, as I've told more general audiences, it's like the thing about asteroid impacts is that they've happened to us over the eons. Oh, by the way, this is an astrobiology talk. I should have linked it to astrobiology. Impacts, of course, have changed the life on our planet dramatically. The dinosaur related impact, whether it actually ultimately wiped them out or not, is still a matter of debate, but it's certainly probably an element. We are now in the generation where we can actually prevent that in principle. So we can prevent a natural disaster. We can't stop earthquakes and hurricanes and stuff like that, but we could in principle protect ourselves from an impactor, which is great. That said, it is not our most existential threat at the moment. That would be ourselves. Questions? Go over here, yes.
Did the tail ejecta go in front of any bright stars for
Oh, yeah. There is some spectroscopy that was done. Gosh, and there are being papers published, but I can't tell you much more than that, and I can't even tell you whether it was absorption or just simply emission. So that's a good point. And actually, there's something related, sort of. Remember how I said that there's ejecta that will have escaped the whole system, right? What that means is the system has a beta, right? So the entire orbit around the sun was changed as a result of this impact. We're not sure by how much, but we can actually measure it using occultations by getting very, very precise positioning of the asteroid. And so people are currently doing that. When you couple those occultations with the upcoming Hera measurements, we'll be able to get the beta value, what we call the heliocentric beta of the orbit change. So kind of related to what you said there. And go ahead, do you have a question? I thought you,
I
I answered, look at me, correct.
All right, maybe one more question.
All right.
Earlier you talked about the contingencies when, satellite was in final approach. And you said you're afraid that some people were going to lock on to the wrong thing.
Yeah,
Could you just talk about that and what?
yeah, yeah, I actually, I have let's see if I can do that really quickly. I have a video showing that. You know what, that could be a little hard to find. So I won't bother showing it, but it's a demonstration of how SmartNav works. And so what the system was doing was taking two pictures consecutively. We take a picture at normal resolution, normal brightness, so that humans could see pretty picture. The next image was deliberately overexposed to see where the light is. And then it did one, then the next, one, then the next. And the SmartNav was using the overexposed pictures to see where the brightnesses were. And then the controllers could see an overlay of what the spacecraft thought was Didymos, what the spacecraft thought was Dimorphos. It was labeling them in real time, 30 seconds delay. And then it had little red circles for anomalies. Right? And these anomalies were things that it was paying attention to see if they would go away. And mostly they would just disappear, then pop up, disappear, pop up, disappear. And the humans were watching to see, okay, is the computer going to decide whether those anomalies is actually the target or not? And that never happened. So everybody's kind of watching, like, hands off, okay, we're good. And the last, so you may have noticed that as we were approaching, there was a little shake. That was because the thrusters were constantly firing to try and make sure that our target was in the sweet spot for the direction of the spacecraft. So remember, everything's kind of not necessarily in a direct line. Right? You're a little tilted. You're trying to get in to do it just right. The last couple of minutes or something like that, they turn off the jets and it's just free flow straight in. So, and it worked. And by the way, it's based on military technology for precision guided missiles. So APL has defense contracts, and so some of that technology was there. So sorry about that.
All right, well, why don't we thank Derek again for a fascinating job?